Hello, my dear students. This is Dr. Rami Khan of Concept Chemistry classes. Today in this video, I am going to explain about P block elements. P block elements are those elements which are present in group 13 to group 18 in the periodic table. Group 13 and 14, they are in 11 standard, while group 15 to group 18, they are in 12 standard. These are in 12 standard. So in this particular video, I am going to cover group 15 only. Group 15 elements are nitrogen, phosphorus, arsenic, antimony and bismuth. Group 16 are oxygen, sulfur, selenium, tellurium and polonium, while group 17 are halogens, fluorine, chlorine, bromine, iodine and statin. Group 18 elements are helium, neon, argon, krypton, xenon and radon. They are group 18 elements. Okay, now group 15 elements, which are called nitrogen family, are also called chalcogens. They are called nicogens. Why these elements are called nicogens? Because they are poisonous, right? They are poisonous, therefore these group 15 elements are called nicogens, while group 16 elements, they are called chalcogens because they are present in the form of ores or minerals, therefore they are called chalcogens, while group 17 elements are called halogens because they are present as sea salts, samudra ka salt ki form the most present however. And group 18 elements are called noble gases or inert gases or zero group elements, since they are very very inert and they do not react with other elements. So I'm going to start nitrogen family now. Okay, nitrogen family. In nitrogen family, let us discuss about atomic radii first. Atomic radii increases from top to bottom generally, and in this case nitrogen then phosphorus. When nitrogen from nitrogen to phosphorus, the increase in size is very large, while from phosphorus to arsenic, the increase is slightly less. From arsenic to antimony, again the increase is less, while from antimony to bismuth, again the size increase in size is again less. There is increase in size, but the increase is less. This small increase in size from phosphorus to arsenic, arsenic to antimony, antimony to bismuth is due to pore shielding by the electrons in D and the F subcells. This is given here. Okay, now let me zoom this area. It is written here. The atomic radii increases down the group, only a small increase from arsenic to bismuth due to pore shielding effect by the DNF electrons. Okay, now let us discuss about oxidation state. Before oxidation state, let me write the general electronic configuration of group 15 elements. Group 15 elements has this general electronic configuration: NS2 NP3. Okay, they have 5 valence electrons, and if these 3 electrons from np, outermost p, n is the outermost shell, and if these 3 electrons from p go out for bonding, then they will show +3 oxidation state, and along with these 3 elements, 3 electrons, if these 2 ns electrons also go out for bonding, then they will show +5 oxidation state. So generally group 15 elements, they show +3 and +5 oxidation states. Now stability of this +3 and +5 oxidation state, let me explain that their stability is very important for the examination. So down the group from nitrogen to bismuth, stability of +3 oxidation state increases while stability of +5 oxidation state decreases. This is due to inert pair effect. This is due to inert pair effect, and the inert pair effect is due to again pore shielding by the electrons in d and the f electrons. Stability of +3 oxidation state increases down the group due to inert pair effect, which is the inability of the 2 outermost s electrons to participate in bond formation. So between this ns and the np, there comes actually dn-1 d10 and n-2 f14 in some cases, in case of bismuth actually. So these electrons, they do not shield the ns electron. So the 2 electrons in ns outermost s orbital, these 2 electrons, they do not have tendency to go out for bond formation. So in the heavier elements, in case of antimony and bismuth, these 2 elements, they show +3 oxidation state only, but they can show +5 oxidation state, but their stability is less. Okay, next point is ionization energy. Ionization energy decreases from nitrogen to bismuth. This is general trend. Next property is chemical reactions. Now with hydrogen, these group 15 elements form hydrides of the formula EH3. Okay, these hydrides are given here: PH3, ASH3, NH3, SBH3, BiH3. These are the hydrides formed by combining with hydrogens. So in these hydrides, they have this generally structure. Okay, let me draw the general structure. This is E, and they have this geometry, and this E, the central atom, has a lone pair of electron. So in exam, the properties of these hydrides are frequently asked. So the first and the most important property of these hydrides is boiling point. Now boiling point, what about boiling point? Boiling point depends upon intermolecular force of attraction. So this intermolecular force of attraction again depends upon molar mass of the substance, and the molar mass increases from NH3 to BiH3, right? So in this case, boiling point must increase from ammonia to BiH3, but the actual order is not like this. The actual order is this one: PH3 comes first, then ASH3, NH3, then SBH3 and BiH3. Now the question can be asked here: ammonia has higher boiling point than PH3 and the ASH3. Why? It is because of hydrogen bond between ammonia molecules. In ammonia molecules, there is hydrogen bonds. So due to that hydrogen bond, which is very strong intermolecular force of attraction, ammonia has higher boiling point than PH3 and the ASH3. But ammonia has lesser boiling point than SBH3 and BiH3 because their molar mass is very, very large. Okay, this is very important for examination. Okay, now next property is bone angle. Bone angle has a regular trend, that is NH3, bone angle of NH3 is largest. This is because this is the structure of NH3. Let me give you the reason for this order. And suppose this is PH3, this is PH3. Bone angle is the angle between two bonding pairs. This is a bonding pair, this is another bonding pair, and the angle between these two bonding pairs is called bone angle. Here also this is the bone angle, right? So in case of NH3, nitrogen has higher electronegativity than hydrogen. In PH3 also, phosphorus has higher electronegativity than hydrogen, but nitrogen has higher electronegativity than PH3. So the pool of these two electrons by nitrogen will be more than the pool of these two electrons by phosphorus. So these two shared pair of electrons come closer to nitrogen. So since these two shared pair of electrons are closer to each other, the repulsion between them is large. The repulsion between them is large. Since the repulsion between them is large, bone angle becomes higher. So bone angle decreases from ammonia to BiH3 due to decrease in electronegativity. You can write, okay, due to decrease in electronegativity from nitrogen to phosphorus to arsenic to antimony to bismuth. Okay, basicity. Okay, basicity is the property of giving out this lone pair of electron to someone, to an acid actually. So nitrogen has higher electronegativity than this phosphorus, so this nitrogen pulls more electrons from hydrogens. So this nitrogen has higher electron density as compared to phosphorus, so it can give out more electrons in comparison to phosphorus. So therefore ammonia has higher basicity than PH3 and rest of the hydrides. Okay, now the last property is bone dissociation energy. BDE is bone dissociation energy. Bone dissociation energy is the energy required to break this bond, NH bond and this PH bond. So this again decreases from ammonia to BiH3. The reason is the increase in atomic size from nitrogen to phosphorus, then arsenic, then antimony and bismuth. Okay, let me explain this. This is suppose nitrogen and this is our hydrogen. Okay, and in case of PH3, this is phosphorus and this is hydrogen. So the bone angle, bone length from here to here is shorter, while in case of PH bone, this bone angle is larger. And in case of ASH3, this would be again larger. So bone length is again higher. So higher the bone length, okay, weaker the bone will be. Therefore the energy required to break this bone will be lesser than the energy required to break this bone. This is in case of NH3, right? So decrease in bone dissociation energy from NH3 to BiH3 is because of increase in atomic size, right? These are some important properties of hydrides of group 15 elements, right? Okay, now let me come to the next property, that is reactivity with oxygen. So with oxygen, these hydrides, these elements of group 15, they form oxides of these two types, E2O3 and the E2O5. For example, I can say N2O3 and N2O5, right? P2O3 and P2O5. Okay, so the pentoxide, this is the pentoxide. The pentoxide is more covalent and more acidic than the trioxide E2O3. As E2O5 has higher oxidation state. In case of N2O3, nitrogen has +3 oxidation state, while in case of N2O5, nitrogen has +5 oxidation state. So due to higher oxidation state of nitrogen, this N2O5 has more acidic as well as more covalent character than N2O3. Okay, now what about if I want to compare the acidic nature of these two pentoxides? So in this case also nitrogen has +5 oxidation state, while in P2O5 phosphorus also has +5 oxidation state. So between these two pentoxides, which one will be having more acidic as well as more covalent nature? That depends upon the electronegativity of this nitrogen and phosphorus. Nitrogen has higher electronegativity than phosphorus, so therefore this N+5 will have higher tendency to accept electron. Acid is that substance which can accept electron, while base is that substance which can give out electron. Okay, so N2O5, in N2O5 nitrogen has +5 oxidation state, and this N+5 has higher tendency to accept electron. So this N2O5 will be more covalent and more acidic nature than P2O5, right? Okay, and the next point in this oxides is this one. Oxides of nitrogen and phosphorus are acidic. These oxides which I have written now, they are acidic in nature, while those of arsenic and antimony are amphoteric. Amphoteric is that property which of elements or of compounds which can show both acidic as well as basic character, right? Or we can you can say which can react with both acid as well as base. And the oxides of bismuth are basic in nature, right? Okay, in oxides of nitrogen, let me mention you one important point, that is N2O. This is nitrous oxide, this is NO, this is nitric oxide, and this is N2O3. Let me write N2O3 first, then N2O4 you can say, or you can just write NO2. These two are same. This is dimer of NO2, and lastly N2O5. These are the oxides of nitrogen actually, and between these five or six oxides of nitrogen, the first two, nitrous oxide and nitric oxide, okay, they are neutral, they are not acidic, they are neutral, while remaining oxides of nitrogen, they are acidic in nature, right? This is also called ha-ha gas, that is laughing gas, okay, ha-ha-ha. Okay, now let me go to the next property, that is reactivity of group 15 elements with halogens. But with halogens, they form two halides, that is EX3 and EX5, right? EX3, let me give one example, PCl3 and PCl5, right? Nitrogen does not show this EX5, means nitrogen has this oxide NCl3, but nitrogen does not have this oxide NCl5, does not exist. This is due to absence of d orbitals in nitrogen, right? So nitrogen does not form pentahalide due to non-availability of d orbitals in its valence shell. Pentahalides, this pentahalide is more covalent than trihalides because of higher oxidation state. Higher is the oxidation state of the central atom, higher will be the covalent nature. Okay, in PCl5 phosphorus has +5 oxidation state, while in PCl3 phosphorus has +3 oxidation state. Okay, these are some important points about these means compounds of group 15 elements. Now let us go to nitrogen. So for nitrogen, nitrogen can be prepared in the laboratory in small amount by reacting with ammonium chloride with sodium nitrite. So our nitrogen is formed. And if we want to prepare pure nitrogen, then we can just heat this compound BaN3 whole twice. BaN3 whole twice is called barium azide. Barium azide, right? So this barium azide, when it is heated, this azide decomposes to barium and nitrogen. So barium will be solid, and the gas evolved will be our nitrogen gas, right? So instead of barium azide, we can also take sodium azide, NaN3. This is our sodium azide, and if it is thermal decomposed, we will get sodium and nitrogen. This will be our valence chemical reaction. Okay, so here are some more reactions from which we can prepare nitrogen. Okay, so let me go to the next point. This is again one more reaction to prepare nitrogen. Okay, next is properties of nitrogen, dinitrogen. Okay, nitrogen is restricted to a maximum covalency of 4. This is very frequently asked in exam, in both CBSE and council exam. The question will be why. So answer will be because only 4 orbitals, 1s and 3p orbitals will be there in case of nitrogen. Only 4 orbitals are available for bonding. Due to this reason, indirectly you can say we do not have d subshell or d orbitals in nitrogen. Therefore, nitrogen cannot have pentavalent or cannot have covalency of more than 4. Right? Question can be anything like that. Okay. Next is next property of nitrogen is formation of nitrites. So we can react nitrogen with calcium, and the mixture must be heated to form calcium nitrite. This is calcium nitrite, and with oxygen, nitrogen forms nitric oxide, and this nitric oxide is formed only if we heat the gaseous mixture at 2000 Kelvin. This is a very, very high temperature, because nitrogen also has, you know, these 3 bonds between the 2 nitrogen atoms, and oxygen also has 2 bonds between the 2 oxygen atoms. So in order to react between these 2 elements, these 3 bonds and these 2 bonds, they have to be broken. So therefore a large amount of energy has to be supplied, right? And one important reactivity of nitrogen is when nitrogen is heated with calcium carbide. This is calcium carbide. Okay, then calcium cyanamide is formed along with carbon. This is calcium cyanamide, CaCN whole twice is calcium cyanide. This is not calcium cyanide, this is calcium cyanamide. So this reaction is important. This has been asked in NEET also. Okay. Next point is anomalous properties of nitrogen, which is very, very important. This I have already given the reason of nitrogen showing anomalous behavior. That important reason is absence of d orbitals. Other reasons for anomalous behavior of nitrogen are its small size, high electronegativity, high ionization energy, and that I have already mentioned, non-availability of d orbitals. Due to these reasons, nitrogen shows anomalous behavior from rest of the members of group 15 elements. Means nitrogen and phosphorus, arsenic, from these rest of the members of group 15, nitrogen shows some different behaviors, from some different characters, you can say, from these elements. That is called anomalous behavior or anomalous properties. Okay, Some examples are given here. Nitrogen forms p pi multiple bonds. Heavier elements of this group, means phosphorus, arsenic, antimony, bismuth, they do not form this p pi bond. Instead of this p pi bond, these elements form d pi p pi bond. Okay, but nitrogen forms p pi bond because nitrogen do not have d bond, d subshell, therefore nitrogen cannot form this d pi p pi bond. Okay. Okay, next important point is nitrogen exists as a diatomic molecule with a triple bond between the two atoms. Consequently, its bond enthalpy, or you can say bond dissociation energy, is very high, that is 941.4 kilojoule per mole, and hence nitrogen is chemically inert. Since its bond dissociation enthalpy is very high, it is very difficult to break this bond, so it requires a large amount of energy. So it is not easy to break this bond, so nitrogen is chemically inert, while rest of the members are not so inert. Okay, these are some properties. Okay, then let us move to the next important topic of group 15, that is nitric acid, HNO3. This is very important. This is industrial preparation of nitric acid, which is called Ostwald's process. First of all, nitrogen is heated with oxygen, that is oxidation, actually combustion, or you can say ammonia, not nitrogen. We can take nitrogen also here, but ammonia and oxygen react somewhat easier. Remember, when nitrogen and oxygen they only react at 2000 Kelvin, right? I have already mentioned, and this is very tough. But when ammonia and oxygen they are reacted, okay, that happens at 500 Kelvin. This is comparatively lesser energy, right? Lesser temperature. Okay, so nitrogen and oxygen they are reacted at 500 Kelvin and 9 bar with the presence of this catalyst, platinum rhodium GAG, and they form nitric oxide. And in the second step, this nitric oxide is further oxidized to NO2. NO2 is nitrogen dioxide, and in the third step, this NO2 is reacted with water to form our nitric acid. So along with this nitric acid, a gas is evolved, that is nitric oxide. So we can collect this gas, and we can continue from the second step to produce more nitric oxide, right? So this is the reason why this Ostwald's process is used as industrial preparation. Industrial preparation is nothing but if we want to prepare large amount of a substance, then we call that kind of preparation as industrial preparation, or you can say commercial preparation. Okay, so in the third step, since nitric oxide gas comes out, so we can collect that gas after collecting this nitric acid. Okay, and the gas can be collected and reused in the second step without going through the first step. Okay, only requirement will be our oxygen, and oxygen is easily available in the atmosphere, that can be collected by fractional distillation. Okay, so this is the industrial preparation of nitric oxide, which is a nitric acid, which is very important for examination point of view. And suppose if we want to prepare some amount of nitric acid in the laboratory, then we can follow this step. Sodium nitrate is reacted with sulfuric acid to form our nitric acid in some lesser amount. Okay, then next is our properties of nitric acid, which is not so important. Please note down this also. Now let us move to the next point of this nitric acid, that is reactivity with metals and reactivity with non-metals. Okay, with metals there are two important metals which will react with nitric acid. These two elements are copper and zinc, right? Copper and zinc. This is also copper, this is also zinc. So nitric acid reacts with copper differently. If we take dilute, then a different product is formed, and if we take concentrated acid, then concentrated HNO3, then a different product is formed. Okay, so let me explain that. In the first reaction, copper is reacted with HNO3. In the second reaction, copper is reacted with HNO3 again, but in the second case, HNO3 is concentrated HNO3, right? So these two reactions are with zinc, and these two reactions are with copper. Okay, so let me give you the easy way for these reactions. Okay, with dilute HNO3, copper gives copper nitrate and water. The reaction terminates here. Actually, this is the second reaction of copper, not from here. Okay, copper and the concentrated HNO3, this is the second reaction. Second reaction starts from here, first reaction end here. Okay. Okay, now copper nitrate and water with concentrated HNO3, also again copper nitrate and water. This is third reaction, starts from here. Okay, now with zinc, dilute HNO3 reacts to form zinc nitrate and water along with one. Let me simplify this reaction. This is copper, again copper, then zinc, again zinc, and if it is reacted with HNO3, and this is our dilute, right? And this is reacted with HNO3, and in this case this is our concentrated HNO3. Again zinc reacts with HNO3 dilute, HNO3 concentrated, right? Now in this case, in all the cases, two products are common, that is copper nitrate, zinc nitrate. Okay, these are given in the reactions. Okay, zinc nitrate, copper nitrate, zinc nitrate, and the second product, common product, will be water. In all the four reactions, water will also be produced. The difference is the oxide of nitrogen produced in this reaction. Okay, in the first case, when copper is reacted with dilute HNO3, NO, nitric oxide, is produced, while in case of concentrated HNO3, NO2 is produced. With dilute HNO3, N2O, nitrous oxide, is produced, while with concentrated HNO3, zinc produces NO2. So let me make these reactions easier. With concentrated HNO3, the oxide produced are, nitrogen dioxide, right? Nitrogen dioxide. In both cases, nitrogen dioxide is produced with concentrated HNO3, while with dilute HNO3, copper produces nitric oxide, while with zinc produces nitrous oxide. This is the way to memorize this reaction. Okay, in all four cases, with copper nitrate will be formed. This is for copper nitrate, while with zinc nitrate will also be formed, right, along with water. Here also water. Okay. Now let me move to the next property. This is with non-metals. Now there are four non-metals, important non-metals: iodine, carbon, sulfur and phosphorus, and they react with nitric acid. In this case also, nitrogen dioxide and water. Nitrogen dioxide, water. Okay. Okay. With sulfur also, nitrogen dioxide and water. With phosphorus also, nitrogen dioxide and water. These are common byproducts, okay, or common products. With iodine, we get iodic acid, HiO3. With carbon, carbon dioxide is formed. With sulfur, sulfuric acid is formed. With phosphorus, phosphoric acid is formed. Okay, please memorize these reactions. This is again important for examination point of view. Next is Brown ring test. Video sikhara this hange adubu ai sigi kenosimadi cover tawgena khale warabsu wana dum yengbiro. Okay, Brown ring test se nitrogen ko nitrate ion present oi the haba confirm tawnaba test amani. In this test, any compound containing nitrate ion, this is nitrate ion, NO3 minus, this can be copper nitrate, this can be nitric acid, HNO3. Okay, this can be sodium nitrate. Aduga kanaga reaction tonba Fe2 plus amaga reaction tonba. Fe2 plus amaga reaction tonba habidi kaino any salt solution containing this Fe2 plus ion, ferrous ion. Okay, this can be FeSO4. Okay, for example, and in presence of an acid reaction tohanba matamda, then we will get our nitric oxide. Then Fe2 plus is oxidized to Fe3 plus and along with water. Now this nitric oxide is reacted with this complex FeH2O whole 6 2 plus, and this complex is formed. In this complex, one of the water is displaced by NOS ligand. So this complex, the color of this complex formed will be brown. Okay, so if brown ring in the form of a ring, right, in the form of ring, this will be appeared, and if some brown ring test is appeared, then the compound contain nitrate ion, right. This is brown ring test, and this has been asked in council exam also. Okay, next is ammonia. Ammonia in the laboratory, ammonia can be prepared by reacting ammonium chloride with sodium hydroxide. Ammonia is formed, and this can be prepared by reacting magnesium nitride with water. Ammonia is formed. Here also ammonia is formed, and this is the industrial preparation for ammonia, that is called Haber's process. Nitrogen and hydrogen gas, they are heated at 700 Kelvin at a pressure of 200 Pascal, 200 into 10 power 5 Pascal, that is 200 atm approximately, or 200 bar. And the catalyst used in this reaction is iron oxide with small amounts of K2O and the aluminum oxide. These oxides acts as promoter, and the iron oxide as catalyst, right. And these three are optimum conditions of Haber's process. Again, important reaction, important of council exam and the CBSE. Okay, so ammonia is basic in nature. This nitrogen has a lone pair of electrons, so this can be given to water to form ammonium hydroxide. In the chemical properties of reaction, these first two reactions are important. When ammonia is taken in excess and if it is reacted with chlorine, then two compounds are produced, that is ammonium chloride and nitrogen. And please observe here, if ammonia is taken in excess, then both the products contain nitrogen, right. And if chlorine is taken in excess in this reaction with ammonia, then NCl3 and the HCl are formed. And again, notice that in the two products chlorine is present. Okay, so these are some other reactions of ammonia. These are complex formation of ammonia by reacting with these ions. These are precipitation reaction when ferric chloride is reacted with aqueous solution of ammonia. Aqueous solution of ammonia is here. Aqueous solution of ammonia produces ammonium hydroxide. This is ammonium hydroxide, that is aqueous solution of ammonia. Okay, then a brown PPT is formed. With aluminum chloride, white PPT is formed, right? Similarly, with this CrCl3, sorry, a green PPT is formed, right? Next important property, next important part of this video is phosphorus, allotropes of phosphorus. This is important. In allotropes of phosphorus, we have two important allotropes, that is white phosphorus and red phosphorus. Black phosphorus is not so important. Sidayda translucent oiba ko, translucent oiba, aduga white wax sea solid oil. This is extremely reactive. White phosphorus is extremely reactive, and this is poisonous. And this white phosphorus is not soluble in water, but it is soluble in carbon disulfide. This is important property of white phosphorus. And difference between white phosphorus and red phosphorus can be asked in the exam in terms of solubility or in terms of reactivity. Okay, this glows in dark. If we place in a dark room this white phosphorus, then it will glow. That is called chemiluminescence, right? Red phosphorus sina white phosphorus tagi 573 Kelvin heat tum phangeba. Other laite manam laite ko ma poisonous oide. Water da as well as kaida carbon disulfide soluble oide red phosphorus. So this property and this property, they can be asked in the exam in the form of comparison. Okay, red phosphorus is found in the form of polymeric chain, right? While black phosphorus has two forms, alpha black phosphorus and beta black phosphorus, right? This is not so important, but please note down these points also. Okay, next is compounds of phosphorus, that is phosphine. Phosphine is pH3. These are some preparation reactions of phosphine, and these are some properties of phosphine. Holmes signal is that signal which is being used in sea when some you can say ship is in danger. They give out some signal. That signal is called Holmes signal. Okay, and that signal phosphine is used. Okay, next important point about this compounds is compounds of, you can say, group 15 elements, phosphorus halides. And in phosphorus halides, for example, I can just write PCl3 and PCl5, right? So these are the some preparation reactions of these halides PCl3 and PCl5 by reacting phosphorus with chlorine and SOCl2. SOCl2 is thionyl chloride. Okay, then next are the properties of these halides of phosphorus with water, with acetic acid. This OH, this is an organic reaction in which CH3 C double bond O OH is reacted with PCl3. Then this OH is being replaced by Cl. So this is our product. This is acyl chloride, or you can say acid chloride. This is here. Okay, with silver, with tin, with here are some reactions. And when this is also again important reaction, what with the question can be like this: what happens when PCl5 is heated? So you can answer, when PCl5 is heated, it decomposes into PCl3 and chlorine. So you can write this reaction. Okay, now the last topic of this video and this nitrogen family is oxoacids of phosphorus. Again, this topic is important, oxoacid of phosphorus. Okay, these are the some oxoacids of phosphorus: H3PO2 hypophosphorus acid, H3PO3 phosphorus acid, H3PO4 orthophosphoric acid, H4P2O6 hypophosphoric acid, and there are also some oxoacids of phosphorus, H4 H4P2O7 pyrophosphoric acid, HPO3 metaphosphoric acid. This can be written in a better way like this. Okay, now in exam question can be the basicity of these oxoacids, right, and structure can be asked in the exam, right, structure. So here are some structures of these oxoacids. These are some structures which can be asked in the exam. This is phosphoric acid. There is a phosphorus oxygen double bond and OH. So basicity is the number of replaceable hydrogen, and those hydrogen can be replaced which are attached to oxygen directly, right? So basicity of this orthophosphoric acid will be 3, and this is our phosphorus acid, or you can say orthophosphorus acid. Out of these 3 hydrogens, only 2 hydrogens are attached to oxygen, while this hydrogen which is directly attached to phosphorus, this is not ionizable. So in basicity we must include only these 2 hydrogens. So basicity of this phosphorus acid will be 2, and this is hypophosphorus acid, and in case of hypophosphorus acid, basicity is only 1, since this hydrogen which is attached to oxygen can only be displaceable, while these 2 hydrogens are not displaceable. Okay, one important point in the this is another structure of H4P2O7. H4P2O7, all the 4 hydrogen atoms are attached to oxygen, so basicity of this oxoacid of phosphorus will be 4. Okay, so now one important question that can be asked in the exam is reducing nature. So by explaining this, after explaining this point, let me end this video for today. Now, reducing nature of oxoacid of phosphorus depends upon the number of pH bond, directly proportional, you can say, pH bond. Here is the number of pH bond, here will be its reducing nature. So in these 2 oxoacids of phosphorus, in these 3 oxoacids of phosphorus, number of pH bond is highest in this hypophosphorus acid. 2 pH bonds are present here, while in orthophosphorus acid only 1 pH bond is present. So between these 2 oxoacids, reducing nature will be higher for this H3PO2. Okay, while order can be like this: H3PO4 dagi, H3PO3 niheli, then H3PO2 lakane. This will be the order of increasing order of reducing nature of these oxoacids. Okay, for today let me end this video. Thank you for bearing with me. Please like this video, share to your friends, and if you are new to the channel, please subscribe to the channel. Thank you.